Got a fun video for you guys today. I thought it would be interesting to see how Systems Toolkit stacks up against the current champion of having fun in RPO, which is Kerbal Space Program. Obviously, the cost difference between these two programs is astronomical, no pun intended. So much so that it is very difficult for a standard user who is not engaged in education or industry to get ready access to everything Systems Toolkit has to offer, especially when you're looking at advanced modules like Astrogator. Whereas KSP is frequently available on Steam for well under $20 and is worth every penny, trust me. So I thought it would be interesting to see if we can determine the actual bang for buck that we get out of Systems Toolkit versus Kerbal Space Program. We're going to be using our standard RPO satellite, so we've got our reference satellite centered over 0 degrees longitude of the ascending node, and our chase vehicle 1 degree away, and we're just going to have chase go 1 degree over to reference satellite. And you can see we've got the exact same setup in Kerbal Space Program right now, so we've got the chase satellite 1 degree away from the reference satellite, currently at 0 degrees longitude. In order to give Kerbal a fighting chance, I'm using a mod known as Realistic Solar System that takes what is traditionally the Kerbin Earth and turns it into the actual Earth with actual Earth physics. So everything that we're seeing from the semi-major axis and eccentricity should be relatively similar to what we see in STK in terms of distances. And sure enough, you can see chase is currently at our geo rule of thumb 735.93 kilometers away, and reference satellite is 735 and some change away from its Kerbal Space chase. Okay, so that's how we've modded KSP to be a lot more like STK, but we also have to go in and model STK to be like KSP. So first we're going to be modeling a satellite, really more of a rocket body that looks like this. So we have to take a look at the stats of our Kerbal vehicle and put those into STK for accurate modeling. So here we've got a vehicle that weighs 5.84 tons in Kerbal Space Program, and let's go into our chase vehicle and make it 5.84 tons. We'll just go to the initial state and we'll manipulate its dry mass. Next up, you can see our KSP vehicles are using the LV909 Trusty Terrier liquid fuel engine, which it looks like in vacuum has a thrust of 60 kilonewtons and a specific impulse or engine impulse of 345. Okay, simple enough. We'll just go into the component browser of STK. We'll go down to our engine models. I've already built out the KSP engine here, which you can see currently has 60 kilonewtons of thrust and a specific impulse of 345. So far so good. Looks like everything's being repped accurately. So let's just start doing some maneuvers. We'll go into our astrogator for the chase vehicle. We'll add a maneuver. It's going to be a thrust vector. Kerbal uses VNC, so we'll use VNC. It's going to be a finite engine. We're going to use our KSP engine to model that. Since we're 1 degree away in the in-track direction, we just have to use a standard in-track burn or V burn. And we're just going to set up the duration for delta V, so rather than burn for a specific time, we're going to burn a specific meters per second, and we're going to use our standard rule of thumb. Okay, so we got our delta V, we're going to burn 2.84 meters per second, and we're going to do that all in the in-track direction. Let's go ahead and run it. You should go to our 3D graphics window and see our familiar shape, which is the 1 degree approach over 24 hours. And you can see with that beefy KSP engine, it only took 0.274 seconds to lay down 2.84 meters per second of delta V. Okay, so that's what STK had to offer. Let's see what Kerbal can do. So I've got my chase vehicle, currently 735 and some change away from the reference vehicle. We're going to go ahead and add a maneuver here. And we're just going to do 2.84 meters per second. And sure enough, you can see that the burn time that KSP was able to calculate was 0.3 seconds, just like the chase burn time of 0.274 seconds. So let's go ahead and see if I can provide the precision necessary to actually make that possible. Okay, there's our 2.84 meters per second laid down, and let's see what our final result is going to be. So what you can see in KSP is we do have some intersection points that we've established. Let's see how long it's going to take for us to get there. 23 hours and 59 minutes, so far so good. And our min separation looks like it's going to be 0.4 kilometers or 400 meters. So let's go ahead and watch this happen in action. And here we have our close approach. Wow. 4 meters it looks like, close enough to almost scrape paint. Okay, pretty good showing from KSP. Let's get some more data and do some comparative analysis. So after the burn, we can see that the period that was induced into our Kerbal spacecraft has gone from that 23-hour and 56-minute point to 1 day, 0 hours, 0 minutes, and 9 seconds. Let's see what we saw in STK. So go ahead into our report and graphs manager for the chase vehicle. You can see we started off with a semi-major axis in an orbital period of 86,170.621. Okay, let's convert that into minutes seconds. Okay, so our first orbital period was 86,170, which was 23 hours, 56 minutes, and 10 seconds. Consistent to the same thing we saw in Kerbal. And then post-burn, we're now looking at 24 hours, 0 minutes, and 10 seconds. Within a second of exactly what we saw in KSP. Moving into some of our advanced orbital elements, we can see that pre-burn we had an eccentricity of 0, and post-burn we had an eccentricity of 0.001848. And that's exactly what we see in KSP as well. Not bad by Kerbal Space Program. Alright guys, so the big takeaway that I wanted you to get out of this lesson is that when it comes to getting good at rendezvous and proximity operations, it's not about the $100,000 software that you've got going on under the hood. Getting good at RPO is getting good at physics, and really there's a variety of softwares out there that can provide a physics design environment that can increase the amount of knowledge that you're gaining from these scenarios. I certainly won't contend that Systems Toolkit is a perfect software, though I do think it is very good. But when you compare it to something like Kerbal Space Program that has this high user base and this robust mining environment, it's very easy to say that there are other attractive options out there when it comes to knowledge of rendezvous and proximity operations. And I think it'll be good for us to do another comparative analysis down the road between Systems Toolkit and KSP to see if we're really getting all of that big dollar value out of Systems Toolkit that the software was built to promise. Or if something like KSP might be the actual truth when it comes to a robust RPO design environment. And with that, I look forward to next time.